From simple oscillations to complex approximations. Introduction. Why is our world periodic? We all know that radio waves, or light pulses, oscillate. But did you know that simple polynomial mathematics, the Taylor series, is inherently local? It cannot effectively represent discontinuities or global periodic behavior. Today, we want to see how Joseph Fourier changed our perspective on the periodic world with a controversial idea. In electrical engineering and physics, we deal with recurring phenomena, from a swing of a pendulum to electromagnetic waves. To analyze these behaviors, we have two powerful tools, the Taylor series and the Fourier series. But why did one give way to the other? The Taylor series attempts to approximate a function using polynomials centered around a specific point. As shown in the formula on this slide, the approximation is built on derivatives at a single location. So, what is the problem? First, locality. The Taylor series is only accurate in the immediate vicinity of point A. Second, discontinuity. The Taylor series requires smoothness and infinite differentiability, which discontinuous signals simply do not satisfy. This is where Joseph Fourier enters. He claimed that instead of polynomials, we should use the building block of nature, sines and cosines. Section 1. Anatomy of the Fourier series and its coefficients. Any periodic signal with a period t can be represented as a sum of harmonics. As you can see in the general Fourier series equation on the slide, we decompose any complex function into a combination of sines and cosines. But the fundamental question is, how do we find these coefficients? The key lies in the property of orthogonality. By integrating the product of the function and a sine or cosine over one period, we extract the contribution of each specific frequency. Let's look at what these coefficients represent. The A0 term is the average of the signal, also known as the DC level. The AN and BN coefficients represent the intensity or strength of each frequency present in the original signal. Essentially, these coefficients are projections of the signal onto orthogonal basis functions. In electric field analysis, symmetry is our salvation from long, tedious calculations. Even functions contain only cosine terms, and odd functions contain only sine terms. Recognizing these symmetries in the design of antennas and waveguide cuts the problem-solving path in half for engineers. Section 2. The Gibbs Phenomenon and the Engineering Challenge. Why is it that no matter how many Fourier terms we add, there is still a 9% jump at the edge of the signal? The Gibbs phenomenon isn't just a mathematical error, it introduces ringing, which is a critical factor in circuit switching systems. When you approximate a square wave, extremely common in electricity, with the Fourier series, you see oscillations at the edge. As shown in the graph on your slide, even if you increase the number of terms to infinity, the overshoot remains at about 9% of the jump height. It simply becomes more localized near the discontinuity. In power systems, these oscillations can cause noise or even damage sensitive equipment. Let's apply these theories to a real-world electromagnetic problem. Imagine a rectangular metal channel where 3 sides are grounded at zero potential, and the fourth side is held at a constant voltage V0. Our goal is to find the electrical potential at every point inside this slot. The mathematical challenge is satisfying Laplace's equation. When using separation of variables, the solution naturally appears as a sum of sinusoidal functions. But here's the catch. Our boundary voltage is a constant line, while our functions are oscillating sines. This is where the Fourier series becomes indispensable. We reconstruct the flat voltage line using a combination of different spatial frequencies. using only the first term gives a very rough estimate. But as we add more terms, the electric field distribution aligns perfectly with physical reality. And here is the golden nugget for engineers. Near the top corners, where the voltage abruptly drops from V0 to 0, the Gibbs phenomenon reappears. This reminds us that in high voltage equipment, sharp edges and discontinuities are always where the highest electrical field stress occurs. Section 3, Envelope Approximation, SVEA. How is it possible to solve a phenomenon that oscillates trillions of times per second with a single simpler equation? With the envelope approximation technique, we ignore the fast oscillations to predict the behavior of laser pulses across kilometers of optical fiber. Sometimes, oscillations are so fast that checking each one is impossible or unnecessary. This is where we use SVEA, the slowly varying envelope approximation. In this model, we assume the wave consists of two parts: the carrier, the fast oscillation, such as light or radio frequencies, and the envelope, the core information that changes slowly. As you can see from the mathematical expressions on the slide, we decompose the electric field into the product of an envelope and an oscillating wave. The core assumption is this: the envelope changes very little over the distance of a single wavelength or period. By applying this constraint and neglecting second-order derivatives, the complex second-order wave equation reduces to a simple first-order transport equation, shown at the bottom of the slide. This provides two vital engineering insights. First, propagation speed. The information or envelope moves at the group velocity vg, not the phase velocity. Second, computational efficiency. This approximation makes numerical simulations in fiber optics and laser physics up to 1,000 times faster. By reducing the complexity of the differential equations, we effectively ignore the quadrillions of oscillations happening underneath to focus on the pulse itself. Section 4. Why Fourier is the best and what are the limits? But be careful. Every approximation has a limit. If your pulse duration becomes too short, all this classical mathematics collapses. Let's see where the boundary of the Fourier series lies. First, why does Fourier lead the way in electrical fields and waves? The first reason is minimum error. Among all trigonometric approximations, the Fourier series provides the lowest least squares error, LSE. The second reason, which is fundamental, is the concept of eigenfunctions. Linear media, like air or copper, do not change the frequency of a sine wave, they only affect its amplitude and phase. In simple terms, a sine wave goes in and a sine wave comes out. So, where is the limit? We are permitted to use these approximations only as long as the omitted harmonics do not contain significant energy. Furthermore, at extremely high frequencies, such as ultra-short laser pulses, the envelope approximation SVEA is no longer valid. Why? Because in this regime, the envelope changes just as fast as the oscillation themselves. The distinction between the carrier and the envelope disappears, and our classical mathematical framework reaches its boundary. Conclusion. The Fourier series is not just a formula, it is the language through which nature speaks. From noise analysis in a simple circuit to the propagation of light pulses in the depths of the ocean, everything is owed to our understanding of these harmonics. Thank you so much for watching. I hope this deep dive into oscillations, complex approximations, and their engineering applications was helpful. If you want to explore more about how mathematics fuels modern engineering, make sure to subscribe to our YouTube channel and hit the notification bell. For more in-depth tutorials, technical articles, and resources, don't forget to visit our website. We have a lot of more exciting content coming your way. See you in the next video.